Did you? All right, so I'm going to get started. So I'm recording this, by the way. The 8-note interval on a keyboard, I don't know if you guys play piano or not, but there's a pattern that repeats. So if you go to middle C, right, on a keyboard, and I count over 1, 2, 3, 4, 5, 6, 7. Well, somehow I screwed up. You go 1, 2, it's 8 keys in between. 1, 2, 4, 5, 6, 7, 8. So every 8 keys, there's a pattern that repeats, right? The periodic table is very similar to that, all right? How is the modern periodic table organized? Well, basically, it's organized so that the elements are arranged in an atomic number and the properties repeat in a predictable way. Ironically, they count by 8s. We go by the valence electrons, and we go by the valence electron is how many electrons they have in the outermost ring. So group 1 has 1 electron, group 2 has 2 valence electrons, and group 8 has 8 valence electrons. So this is what the modern periodic table, this is what it looks like, okay? And this is based on the number of, the atomic number, which is actually the number of protons. So this one right here, this is 1 proton. Way over here is 2 protons, 3 protons, 4 protons, 5 protons, 6, so on and so forth. Okay? So each row of the table of elements is a period. The hydrogen is the first element in period 1. So this is, the rows are the periods. So this is period 1, this is period 2, this is period 3, period 4. Okay? We're going to learn about what that means. Now lithium, the first element in period 2, has an electron in its first energy level. Or no, it's second energy level. I'm sorry, I'm reading this differently. Hydrogen has 1 electron, 1 valence electron in the outermost level, but it only has 1 electron, so that 1 electron is in the first energy level. Now lithium has 3 electrons total, so 2 are in the first energy level, and 1 is left over in the second energy level. If you skip ahead to sodium, sodium is in period 3. It has 1 electron in the third energy level. So this pattern repeats. So the period talks about how many energy levels it has, and the group tells you how many valence electrons it has in that outermost level. Okay? So the groups have a similar electron configuration. So the members in a group in the periodic table have similar chemical properties. So what you're going to learn here shortly is that chemicals interact with each other, elements interact with each other based on this number of valence electrons in most cases. We like to have 8. So sodium chloride, sodium is in group 1. That means it has 1 valence electron. Chlorine has 7 valence electrons. So those two interact because they like to have 8. Okay? So does anybody here know what sodium chloride is? Table salt. Table salt. Okay? So anyways, this pattern of repeating properties, we call it periodic law. Remember, in science, anything that's a law is something that you can't prove wrong. So the atomic structures and the way that we organize them in the periodic table, we call it a law because, well, they started this about 150 years ago, and we haven't really found anything wrong yet. And now the science is really intense. They have particle accelerators. We explode protons and stuff like that, and this stuff hasn't changed. Okay, so the periodic law in the periodic table, this is what you guys are used to seeing. It really is more like this, but could you imagine how big that poster would be? So they take a chunk of that. These two things, these 2 rows fit in here, and that's okay, but that's how they have it set up. So what does the atomic mass of an element depend on? The atomic mass is the value that depends on the distribution of the element's isotopes in nature. Okay, most masses have an isotope. We're going to learn about, I think it's chlorine. Chlorine it normally has 35, an atomic mass of 35, but there's 2 types of chlorine. There's chlorine 35, and then there's chlorine 37. And you might say, well, what's the difference? Well, actually, wait till we get to it. So the atomic mass units, basically, a scientist assigned 12 atomic mass units to carbon-12, which has 6 protons and 6 neutrons. The atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom. So these numbers, the atomic mass unit, is based on 1/12 of whatever the mass of a carbon is. So here, let's learn a little bit about the information on the periodic table. The first number on the top is the atomic number. That is the same number of protons. This is the symbol, right? So this is chlorine, but when we do a bunch of chemical equations and balancing chemical reactions, we would just write Cl, because you don't want to write chlorine every time. Okay. Then the element name, this is chlorine. And then this is what I was talking about. This is the atomic mass. Notice that the atomic mass is not a perfect integer. It's not just plain old 35. It's 35.453. There's a reason for that. Now, the reason for that is there are 2 natural isotopes of chlorine. There's chlorine 35. Chlorine exists in a way that there are 35. That number comes from 18 neutrons and 17 protons. Now, chlorine 37 has 17 protons and 20 neutrons. Okay? So that number of 35.53 or 0.453, that is the actual average. In other words, here's a breakdown. When you think about the distribution of chlorine in nature, about 75% of it is chlorine 35. So that has an atomic mass of pretty close to 35. Chlorine 37, about 22% of, or 24% of that has a mass of close to 37. So when you do all the math, you get 35.453. Okay. What categories are used to classify elements in the periodic table? Well, we say metals, nonmetals, and metalloids. Okay. Basically, we focus on metals a lot because they can conduct electricity and they can conduct heat. And then the less metallic something is, the stricter the label. Metalloids kind of have like some metal properties, but they're not as good as metals. And nonmetals just aren't good for certain things. All right. So the periodic table presents 3 different ways to classify elements. State is one way to do it. It's a solid black symbol. A liquid, and this is referring to room temperature, is a purple symbol. Okay. A gas is a red symbol. Occurrence in nature, elements that do not occur in nature usually have a white symbol. Those are byproducts of something or another thing that we sometimes refer to them as man-made elements. They're not natural. You don't naturally see them. I got to back up on that. Well, anyways, let's not focus on that too much. General properties: metal, blue background; non-metal, yellow background; metalloid, green background. So if I go back to this, let me go back to the slide. This is what they're talking about. The letters are black, right? Or red, or purple, or white. The background can be this color: green, blue. And so if we fast forward, what does that tell us? Oops, I went too far. Those are just the properties of how they classify it. Black symbol means it's a solid. Purple symbol means it's a liquid. Red symbol means it's a gas. If it's a white symbol, it doesn't occur in nature. The background, blue background, means it's a metal. Most things are metals. Non-metal is yellow, and a metalloid is green. So let's go back and look at that real quick. So all this blue stuff is a metal. The green stuff is the metalloids, and that's supposed to be yellow, but it looks more orange to me. If it's black, it's a solid at room temperature. A liquid was, I can't remember what a liquid was. White means that it's a, I think purple was a liquid. And white means that it doesn't occur in nature, and if it's red, it's a gas. Okay. So that's what that means. All right, metals are elements that are good conductors of electricity, except for mercury. Mercury is a liquid at room temperature. Remember that with a liquid, the electrons, not the electrons, but the atoms are further apart, less fixed. So that's why it's not the greatest conductor. Most metals are malleable. That means we can bend them, fold them. That's useful. They're also ductile, so that means that you could make thin wire. So copper is a very soft metal. You can bend it. And that's great for wire because you can bend the metal. So when we break copper wiring, all the electricity in this school has copper wiring. Okay, you can bend it. That's also why it's nice to use for plumbing. You can kind of bend it a little bit. So it's good, and it conducts electricity. So classes of element. A magnesium reacts with oxygen. A dull layer forms on its surface. The layer can be removed to reveal magnesium's shiny surface. So on A, as you see here, if you leave it out in nature, it gets dull and dark. But if you shine up, and it's just a chemical reaction with the oxygen, it oxidizes. But it's right back there. If you remove that oxidation process, you get that. The Statue of Liberty, similar thing. It's not naturally green. That's part of the oxidation process. Many telescopes and mirrors are coated with aluminum to produce a surface that reflects light extremely well. So here's an example of a mirror. Look at how big that thing is. It's just coated with aluminum. Okay. Metals, groups 3 through 12 are called transition metals. Basically, as we move further to the right on the periodic table, it's less metallic. In that group range is copper and silver. Those are some of the first elements ever discovered. One property that many transition metals have is they have distinctive colors. So silver looks like silver, copper looks like copper, right? The compound of oxygen is a transition element, the compound of oxygen and the transition element, erbium, is used to tint pink glasses. So a lot of the things that we see with color is based on what reflects. This is a complicated process. I'll explain it real quick, and we'll talk about it more when we get to the physics sections of the course. This piece of paper reflects blue. Now, what happens is light is electromagnetic radiation. That's an energy. The energy gets absorbed by the material in this paper. The electrons enter into a higher energy state. They don't like being in a higher energy state, so they release energy. This is going on nonstop. Light shines on this, absorbs the energy, releases energy, releases energy. That releases energy in a frequency. That frequency is a wavelength. There's a mathematical relationship. That wavelength is a color. Okay? This piece of paper that's yellow releases that energy at a different cycle than the blue. This is all based on atomic structure. How many atoms, how many valence electrons you have, how easy it is for the electrons to maneuver and release the energy. That's why elements have certain colors. Okay? Nonmetals. They're not great conductors of heat or electricity. They usually have low boiling points. Most of them are gases at room temperature. If they're not a gas and they're a solid at room temperature, they're pretty brittle. You could crack it, break it. They're not malleable at all. Fluorine is the most reactive nonmetal. The gases in group 18 are the least reactive. Now, group 18, because it ends in 8, means that it has 8 valence electrons. That makes sense? In the outermost ring. So some toothpaste use a compound of nonmetal fluorine and a metal sodium to prevent tooth decay. So the fluoride that they put in toothpaste prevents tooth decay. Now, metalloids, elements are located in the periodic table between the metals and nonmetals. See that little diagonal orange line up there on the poster? Mm-hmm. Anything that touches that orange line is kind of a metalloid. Metalloids can conduct electricity, but sometimes they're not the greatest at it, but they're able to do it. Silicon is interesting because we use that in all electronics. All of your guys' cell phones has silicone, which is a compound that has silicon in it. Germanium is also a good insulator for low temperatures and good conductors at high temperatures. So because they're in the middle, depending on what you use them for, their physical properties. 1 year I did research at Northwestern, and there was a carbon-based mono layer study where all Mr. Adams did was they had these very thin layers of carbon on a sapphire substrate, and we just hit it with light and lasers to see what it would do. So those characteristics, and by the way, that same research, you ever seen the Google glasses? So there's things that you could do based on the properties, and the properties of the elements are based on the atomic structure. That's where we're going with all this stuff. Okay, and there's an application. Sometimes you don't want all the electricity to go through. What makes silicone nice, which is a substance that contains silicon, is that it can conduct electricity, but it doesn't do it as quick as, say, copper. So that's great for electronics because you can manipulate it a little bit better. There's copper in there too, but it depends on the application. So it says, how do properties vary across a period in the periodic table? Well, across the period from left to right, it becomes less metallic. So see all the green stuff over there? That's the metals, all the way to the left, group 1, group 2. And as you move all the way over to group 18, they become less and less metallic. So left to right, period 3. Now this is just row 3 on the periodic table, and then group 1 and so on and so forth. Sodium is a metal. Magnesium, less metallic. Aluminum is still, well, magnesium is a metal. Aluminum is a metal. Silicon is kind of a metalloid sort of thing. Phosphorus is a nonmetal. Sulfur is a nonmetal. Chlorine is a nonmetal. And argon is an inert gas. So you could see the transition. The first 3 are metals. This one right here is a metalloid. It's not really a metal. It's not a nonmetal. It's somewhere in between. And then the last 4 are nonmetals. So sodium reacts violently with water. Violently. If I had pure sodium and I put it in water, it would go crazy. Ironically, though, sodium chloride, which is sodium and chlorine, that's table salt. And I put salt in water all day long. Magnesium will not react with water unless the water is hot. So it needs a little extra energy to spark that process. Aluminum does not react with water, but it does react with oxygen. Silicon is generally unreactive. Phosphorus and sulfur do not react with water, but they do react with oxygen. They'll burn. Chlorine is highly reactive. Argon hardly reacts at all. Argon is what we call a noble gas. It has 8 electrons, 8 valence electrons, and that's why it doesn't react with anything. It doesn't need any electrons. Remember, 8's the magic number in that outer ring. So here's some questions we could go through real quick. What determines the atomic mass of an element? A, B, C, or D? You guys read them and tell me. How many of you guys guessed B? The natural distribution of isotopes and the masses of these isotopes. Which of the following is not a characteristic of metals? D? Yep, D. They're not brittle. They're malleable. You can bend them and move them. Now, some of them are strong, like steel. But what happens if you heat up steel? You can bend it. What happens if you heat up, I gotta think of one. Well, ceramic is a compound. It's not brittle. Within a period of the periodic table, how do the properties of the elements vary? Yes. You think it's B?
Wait. Yeah.
You are correct. It becomes less metallic as you go from left to right. And that it's completely based on the atomic structure. In the modern periodic table, elements are arranged in order of increasing atomic mass. True or false? True. No, false.
Oh.
That's atomic number, not atomic mass. That's okay. I got slipped up there too. Did I say atomic mass or atomic number? I kept thinking atomic number. Even Mr. Adams has to read the question carefully, right? And that's it for today.